Hello there, my name is Emma Griffin, and welcome to the wonderful, exciting world that is chemical equilibrium. Now, to begin with the topic of equilibrium, we must review the equilibrium constant. It's funny because equilibrium is not very constant. It's defined as the state when the rate of the forward reaction equals the rate of the reverse reaction, and at equilibrium, the concentrations of products and reactants are constant. This equilibrium is represented by the constant Kc. It is integral to note that Kc can only be measured when the reaction is at equilibrium. Now, if we look at the given equation here, the AA plus BB yields Cc plus DD. This is going to be the equation for Kc, and you're going to have the products divided by the reactants. Now, an important thing to remember when calculating Kc, changing the temperature will change Kc. We will talk a little bit more about that later. Also, pure solids and pure liquids are not part of the equation. They're very excluded. Kc is typically written without units, and the coefficients are written at the lowest possible value. Now, another player in this equilibrium game is the equilibrium quotient, represented by the variable Q. Now, Q is calculated the same way as Kc, so when given this equation, this is how Q will be calculated. It can be used to determine the direction that a reaction is going to shift, like a little chemistry fortune teller. And now, knowing what we do about Kc and Q, what if they're equivalent? Then what? Very good answer. It's going to be equilibrium. Now, what do the magnitudes or values of each of these variables mean? If the equilibrium constant is greater than 1000, then mostly product species will be present at equilibrium. If it is smaller than 0.001, then mostly reaction species will be present. If Kc is between those two benchmarks, then a significant concentration of both species will be present at equilibrium. And to return to the fortune teller Q, if the constant is greater than the quotient, then the reaction will proceed forwards, favoring the conversion of reactants into products. If the constant is less than the quotient, then what? You guessed it, the reaction takes a 180, proceeding backwards and favoring the conversion of products to reactants. And if they're equal, equilibrium. Yeah. Now, Le Chatelier's principle, though it sounds like a silly French guy who made a chemistry rule that we follow for some reason, that's actually exactly what it is. He basically found out that if a certain stress is placed on a system, it will cause a shift in reaction to the right or to the left, kind of like a seesaw. If a stress like an increase in temperature is put on a system, the reaction will shift away from the heat so that the exothermic reaction is favored. Similar to the seesaw, actually. If two people are on it and an extra person goes to the left side, the right side will go up. Three important factors to consider in Le Chatelier's principle are concentration, temperature, and pressure. An increase in concentration results in the equilibrium shifting away from the substance, and the same goes for temperature with the increase in heat. A decrease will cause the equilibrium to shift towards the substance or heat. In the case of pressure, an increase results in the shift towards fewer moles, and the decrease pushes equilibrium towards more moles. Now, these are important to remember because as you start to kind of manipulate equilibrium equations, these three factors are very important to consider. And knowing what we do about Kc and Q, that rhymed, let's evaluate the reaction between sulfur dioxide and oxygen, resulting in the production of sulfur trioxide. For this equation, we are to assume that temperature and pressure are constant. Now, beginning with these concentrations, let's calculate Kc to determine whether the products or reactants are mostly present at equilibrium. I'll give you a second to take out your calculators and determine the equilibrium constant. Okay, so since we have found out that Kc is between 0.001 and 1000, what can be assumed? That's right, there are significant concentrations of both reactant and product species at equilibrium. Now we are going to measure different concentrations of the same reaction, assuming that the temperature and pressure remain the same. With these concentrations, let's set up our formula to calculate Q. Using the concentrations above, I'll give you a moment to make the final calculations, so feel free to pause, or I'll just sing the Jeopardy theme song again. Yep, you guessed it. The result is the same as Kc, even though different concentrations were present. Since Kc is equivalent to Q, this means that the new reaction is also at equilibrium. Now, I know what you're probably thinking. Emma, you sound really psyched about equilibrium, but realistically, what is it useful for? Like, what is it good for other than trying to manipulate an equation to help a farmer produce certain amounts of industrial ammonia? That's a great question. Well, our life is actually dependent on it. The constant uptake and release of oxygen to and from parts of the body is reliant on chemical equilibrium. And without that, the changes of oxygen's partial pressure, which facilitates gas exchange, wouldn't necessarily be able to happen, especially when you're trying to maintain your own homeostasis under certain external conditions that you can't necessarily control. Okay, so what I did here is I just did a quick calculation of blood O2 and hemoglobin concentrations to find the actual concentrations that we can use to find the Kc for the reaction. So what I did is found the bound oxygen, aka oxyhemoglobin, the dissolved oxygen, aka the oxygen gas that's floating around, and the hemoglobin concentrations so that we can use them to calculate our Kc. Okay, so here we go. We have our Kc set up here, the regular equation, and we have inputted our values that we found on the last slide and completely slaved over those calculations, but it's fine. And our Kc value is going to be greater than 1,000, which means that mostly what species are going to be favored? That is correct. Mostly the product species are going to be favored. Woohoo! Okay, now here's a cool little thing called an oxygen dissociation curve. And this shows the relationship between oxygenated hemoglobin, aka oxyhemoglobin, and partial pressure of oxygen in the human body. This is to show the equilibrium of both oxyhemoglobin and hemoglobin at many different partial pressures of oxygen. Now, when oxygen has a high partial pressure, hemoglobin attaches to it, creating oxygenated hemoglobin. This causes a right-way equilibrium shift, since increasing the reactant causes the whole system to shift to the product side, and oxygenated hemoglobin reaches a harmonious equilibrium. In the body, when an erythrocyte or a red blood cell travels to oxygen-deprived tissues, oxygen partial pressure decreases, resulting in the release of oxygen by oxygenated hemoglobin, forming pure hemoglobin, and allowing the oxygen to be released to the places in the body which are lacking oxygen. This engenders a left-way equilibrium shift because of the decrease in reactant concentrations, making the system accommodate to replace the oxygen. In this real-world example, Le Chatelier's principle are applied to increase oxygenated hemoglobin and transport oxygen to oxygen-lacking areas. Now, if we look back and reference this graph, you can also see that as it starts to approach about 85%, the equilibrium is reestablished, as the partial pressure no longer impacts the shape of the curve. It's called the Bohr effect. Okay, so here's a fun little thing that we're going to do. Let's time travel to 2024. It's almost graduation, COVID has become an endemic, and you and your vaccinated friends decide to go on a vacation to Bora Bora. Now, you could walk or you could swim there, but the most efficient option would be to take a plane. Your friend Mary is worried because she always gets lightheaded on planes, but with your thorough understanding of equilibrium, you explain to her why this is. Now picture this, you're taking off the runway. As the plane ascends to a significant level above the sea, oxygen levels begin to drop. This drop in oxygen relates back to Le Chatelier's principle, since there is a decrease in the partial pressure of oxygen, and equilibrium shifts to the left, which results in a lack of oxygenated hemoglobin. And since hemoglobin is not delivering oxygen to your tissues at its regular rate, your brain is deprived of it, causing you to feel lightheaded. If the partial pressure of oxygen in the cabin becomes very low, fun little masks drop down and you and everyone else introduces new oxygen into their system. This influx of oxygen results in the aforementioned rightward shift of equilibrium, restarting regular production of oxygenated hemoglobin and output of CO2, allowing adequate amounts of oxygen to be delivered to the body once again. Now, after your adventurous trip to Bora Bora, you decide to check out another activity and check it off your bucket list and run a marathon. Before doing this, you decide to see how your body will be responding to the exercise and how equilibrium can be maintained. Very smart. While you're running this marathon, your respiratory rate and your heart rate are going to increase. Your working muscles are moving, generating heat, and creating a need for more oxygen. And according to Le Chatelier's principle, there will be a shift in equilibrium, resulting in a decrease in oxyhemoglobin concentration. This heightened required for oxygen, coupled with the increase in temperature, shifts the reaction to the left. And this is going to, once again, decrease those oxyhemoglobin levels, which is actually very, very common in athletes. Runners will also have a lower hemoglobin level by about 10 grams per liter, meaning that the Kc value would be altered, but equilibrium is able to be restored with both time and rest. Now, thank you so very much for watching. I'm so glad that you were able to come with me to Bora Bora and also, run a little marathon and learn about equilibrium in the process. I hope that you've learned something new about both chemical equilibrium and how it actually impacts our homeostasis on a day-to-day basis. Now, if you would like to, go ahead, run a marathon, see if my theories are correct, make sure to get a blood test afterwards. But thank you very much, and I hope that you're having a wonderful day. Here are my references.